Hello everyone. Today we are discussing about general solution of Bessel equation. We already studied about a particular solution of Bessel's equation x square y double dash plus xy dash plus x square minus p square into y equal to 0. Corresponding to m1 equal to p is Bessel function of first kind of order p, which is denoted by jp of x. jp of x is equal to the summation n equal to 0 to infinity minus 1 raised to n into x by 2 whole raised to 2n plus p divided by n factorial into n plus p factorial. In order to find the general solution, we must construct a second independent solution. That is, a solution is not a constant multiple of jp of x. Any such a solution is called the Bessel's function of second kind. Let m2 equal to minus p. This is the next component of initial equation. We have m equal to plus or minus p. We done with m1 equal to p. So next we try with m2 equal to minus p. But in doing so we have the difficulties in difference m1 minus m2, which is equal to 2p. Then the value of 2p is 0 or a positive integer. So first we want to check p is not an integer. Assume that p is not an integer. In this case we replace p by minus p in the previous derivation. In the previous derivation we have n into 2p plus n an plus a n minus 2 equal to 0. Instead of p we write minus p. Replace p with minus p, we get n into minus 2p plus n into an plus an minus 2 equal to 0. Instead of p we write minus p. Then let p equal to 1 by 2 and n equal to 1. Then the above equation becomes 1 into minus 1 plus 1 into a1 plus a minus 1 equal to 0. Here substitute the value of p and n in the equation n into minus 2p plus n into an plus an minus 2 equal to 0. Then we get 1 into minus 1 plus 1 into a1 plus a minus 1 equal to 0. Therefore, we get a minus 1 equal to 0. That is, this term will be 0. So, remaining a1, a minus 1. So, we get a minus 1 equal to 0. We want a particular solution and letting a1 equal to 0. So, we let a1 equal to 0, which does not affect the whole equation. Because 1 into minus 1 plus 1 is already 0. When we let a1 equal to 0, which does not affect the equation. So we let a1 equal to 0. A similar case occur when we let p equal to 3 by 2 and n equal to 3. Then we choose a3 equal to 0. Then next let p equal to 5 by 2 and n equal to 5. Then we get a5 equal to 0. So it does not affect the equation. So we arrive at the second solution as here a1 equal to 0, a3 equal to 0 and a5 equal to 0. That is, the odd coefficients are 0. So we arrive at the second solution as j minus p of x is equal to summation n equal to 0 to infinity minus 1 raised to n x by 2 whole raised to 2n minus p divided by n factorial into n minus p factorial. Here we have jp of x is equal to summation n equal to 0 to infinity minus 1 raised to n into x by 2 whole raised to 2n plus p divided by n factorial into n plus p factorial. Instead of p, we write minus p. Then we get j minus p of x. Here p is not an integer. So the first term of this series is 1 by minus p factorial into x by 2 whole raised to minus p, because here n equal to 0. So substitute the value of n is 0, and we get the first term is 1 by minus p factorial into x by 2 whole raised to minus p. This is it is unbounded, because we know that minus p factorial is could not be defined. We could not be defined minus p factorial. So it is unbounded near x equal to 0. Since we have jp of x is bounded near x equal to 0, here we get x, j minus p of x is unbounded near x equal to 0. These two solutions are independent. Therefore, the general solution of Bessel's equation of order p when p is not an integer is y equal to c1 jp of x plus c2 j minus p of x. This is our equation A. This is when p is not an integer. Next we check if p is an integer. Then when p is an integer, let p equal to m. That is, m is greater than or equal to 0. So j minus m of x is equal to summation n equal to 0 to infinity minus 1 raised to n into x by 2 whole raised to 2n minus m divided by n factorial into n minus m factorial. We know that this series is not exist from the value of n is 0 to n, because we substitute the value of n is 0 to n. That time n minus m is got a negative value, so it does not exist. It exists only when n equal to m. Then we substitute n equal to m, then this term is 0, so 0 factorial is equal to 1. So it exists, this series is exists only from n equal to m to infinity. Therefore summation n equal to m to infinity minus 1 raised to n into x by 2 whole raised to 2n minus m divided by n factorial into n minus m factorial. When we convert the summation n equal to m to infinity to summation n equal to 0 to infinity, we need only to substitute n plus m instead of n. Then we get summation n equal to 0 to infinity minus 1 raised to n plus m into x by 2 whole raised to 2 into n plus m minus m whole divided by n plus m factorial into n plus m minus m factorial. Here we substitute n plus m instead of n. Then solving this we get summation n equal to 0 to infinity minus 1 raised to n plus m into x by 2 whole raised to 2n plus m whole divided by n factorial into n plus m factorial. And take minus 1 raised to m outside from this equation. Then we get minus 1 raised to m into summation n equal to 0 to infinity minus 1 raised to n into x by 2 whole raised to 2n plus m divided by n factorial into n plus m factorial. Therefore we get j minus m of x is equal to minus 1 raised to m into jm of x. Jm of x is summation n equal to 0 to infinity minus 1 raised to n into x by 2 whole raised to 2n plus m divided by n factorial into n plus m factorial. That is j minus m of x is not independent of jm of x. So y equal to c1 jm of x plus C2 into j minus m of x is not a general solution of Bessel equation. To solve this complication, we define the standard Bessel function of second kind, that is yp of x is equal to jp of x cos p pi minus j minus p of x divided by sine of p pi. So that if where p is an integer, then the value of sine p pi is 0. So it does not exist. Therefore, we take p is not an integer. Then the general solution can be written as y equal to c1 jp of x plus c2 j minus p of x. Because p is not an integer, then the value of p pi is a real number which is less than 1. So we can write this is y equal to c1 jp of x plus c2 j minus p of x. Also, it turned out after detailed analysis that the function we get y m of x is equal to limit p tends to m yp of x, where m is an integer, which exists and is a Bessel function of second kind. So in this case, we have the general solution, that is y equal to c1 jp of x plus c2 yp of x. So this is the general solution of Bessel's equation, Bessel function, if p is an integer or not. It is generally say that y equal to c1 jp of x plus c2 yp of x, whether p is an integer or not. This is our general solution of Bessel's function. Next topic is gamma function. If p is a positive real number, then the gamma function is defined as gamma p equal to integral 0 to infinity t raised to p minus 1 e raised to minus t dt, where p is greater than 0. This is our definition of gamma function. Then we have gamma p plus 1 equal to p into gamma p. Then next we prove this, that is gamma p plus 1 equal to p into gamma p. We have gamma p equal to integral 0 to infinity t raised to p minus 1 into e raised to minus t dt. So gamma p plus 1 is equal to integral 0 to infinity t raised to p plus 1 minus 1 into e raised to minus t dt. And solving this, we get integral 0 to infinity t raised to p into e raised to minus t dt, which is equal to limit b tends to infinity. So we can write integral 0 to infinity is a limit b tends to infinity integral 0 to b t raised to p into e raised to minus t dt. By applying integration by parts to integral 0 to b t raised to p into e raised to minus t dt, we get limit b tends to infinity t raised to p into e raised to minus t divided by minus 1 within the limit 0 to b minus integral 0 to b p into t raised to p minus 1 into e raised to minus t divided by minus 1 dt, which is equal to limit p tends to infinity b raised to p into e raised to minus b divided by minus 1 minus 0 plus p into limit b tends to infinity integral 0 to b t raised to p minus 1 e raised to minus t dt. Apply the limit, the first term will be 0 because e raised to minus infinity is 0. So first term is 0, then the second term is p into integral 0 to infinity t raised to p minus 1 into e raised to minus t dt, which is equal to p into gamma p. Here we start from gamma p plus 1 and we get p into gamma p. Therefore, gamma p plus 1 is equal to p into gamma p. And also we have gamma 1 equal to 1, because gamma 1 equal to integral 0 to infinity t raised to 1 minus 1 into e raised to minus t dt, which is equal to integral 0 to infinity e raised to minus t dt, which is equal to 1. Therefore, gamma 1 equal to 1. Similarly, gamma 2 equal to 1 into gamma 1, because we have the result gamma p plus 1 equal to p into gamma p. Therefore, gamma 2 equal to 1 into gamma 1, which is equal to 1, because gamma 1 is 1. And next, gamma 3 equal to 2 into gamma 2, which is equal to 2 into 1, because gamma 2 is 1. So, 2 into 1. Then next, gamma 4 is 3 into gamma 3, which is equal to 3 into 2 into 1. That is 3 factorial. So, we get gamma 2 is 1, gamma 3 is 2 factorial, gamma 4 is 3 factorial, and in general we can say that gamma n plus 1 is equal to n factorial for any integer n greater than or equal to 0. So we got the result gamma n plus 1 is equal to n factorial. And also we have the result gamma 1 by 2 is equal to root pi. It's an important result. Next, a remark. We can define gamma p for negative p's also. We have gamma p equal to gamma p plus 1 divided by gamma p. This is got from here. If minus 1 less than p less than 0, then 0 less than p plus 1 less than 1, so that the RHS of the equation has the negative value. Then next, if minus 2 less than p less than 1, then minus 1 less than p plus 1 less than 0. So we can use the above formula again, define the gamma p on the interval minus 2 less than p less than minus 1. Here we can find that gamma p is positive. This process is continued indefinitely. Then we get limit p tends to 0 gamma p equal to limit p tends to 0 gamma p plus 1 divided by p. That's equal to plus or minus infinity. Accordingly, as p approaches 0 from right or left.